All right, so today we're going to take a look at 7.1, and 7.1 is titled Antiderivatives. And even when we see that title, Antiderivatives, it sounds a whole lot like derivatives, but the opposite of derivatives, which is exactly what it is. And the better we understand derivative rules and remember those, the better we're going to do with antiderivatives. So in order to understand the antiderivative, let's review a derivative. So let's take a function that we're very familiar with, a variation of a power function. Let's say we have the function 1/3 x cubed. Now, if I ask you to find f prime, we can do it very easily. Let's just take a minute and break our power function f apart a little bit. We have a constant of 1/3, and then we have that multiplied by x cubed. If we just have x cubed, the derivative would be 3x squared. But we need to make sure we multiply by that constant. So shortcut, if we bring that 3 in front and multiply, the 3 times 1/3 gives us 1, and our derivative is going to be x squared. So when we go this direction, I like to think about it as moving forward, starting with a function and getting a derivative. What we're going to do is go the other direction. What if I give you the derivative and ask you what the function is? That's saying, okay, let's say I give you this piece and I ask you to recreate this piece. So when we think about it like that, here's what we're going to say. We're going to say 1/3 x cubed is an antiderivative of x squared. Now, a lot of times the book and other calculus textbooks will use lowercase and capital F's to try to distinguish between a function and the derivative. And we'll kind of address that as we need to. But what I want us to think about is an antiderivative tells you what function you need to differentiate to get what we started with. So we need to differentiate 1/3 x cubed in order to get x squared. So we could just kind of re-express it like that. So let me kind of phrase it another way. Another way is to say, let's say you know the derivative of a function. Let's say you know the derivative is 2x. And I'm going to phrase this a little differently. Instead of saying what is f of x, we're going to talk about what is a possibility for f of x. All right, so Lainey, what do you think?
X squared.
Right, so the most common response is x squared, right? Because we're thinking, all right, I already have that 2 that I need. So if I differentiate x squared, I get 2x. Now, this is definitely one that works, right? So here, what we would say about this in the antiderivative language is x squared is an antiderivative of 2x. And sometimes they'll use, for example, if they used a lowercase f instead of f prime, sometimes they'll use an uppercase f for an antiderivative. So I'll kind of give you an example of that notation in the next example. But let's go back and think about another option. So I did on purpose say a possibility, right? Because if we think about other options, this isn't the only option. So if we had lots of people, we might say, well, hey, well, what if we did x squared plus 1? Well, if I differentiate x squared plus 1, I still get 2x because the derivative of that constant term gives me 0. So once we see that that's what's going on, we could create a bunch of possibilities. X squared plus 5, x squared minus 5, as many as we want to. What this is actually telling us is we can think about a more general form, a family of antiderivatives. I think we have someone else beeping in. Okay, we'll give Grant a minute to get in here. Hey, Grant, welcome. Can you hear me? I think Grant is connecting to audio here. There we go. Can you hear now, Grant?
Yep, you can.
Okay, awesome. We were just going over the start of our lesson, so you haven't missed too much. And let's go ahead and recap this one really quickly. You'll be able to catch up super quickly, and then we'll try another example. So to go over this one again, we started with a derivative. And we started with saying the derivative of some function is 2x. What's a possibility for our function? And we're trying to introduce the language of antiderivatives, or going backwards in essence. And in this case, we were able to decide pretty quickly that if the derivative is 2x, the original function had to be x squared, or a variation of x squared. Because if you differentiate the x squared component, you get 2x. And you could actually tack on any constant after, like a +1, or maybe let's write another example. X squared minus 1. And all of these would have, all three of these would have a derivative of 2x. So what this actually leads us to say is anytime we're looking at antiderivatives, we have a family of antiderivatives. And I want to think about what this means visually in just a moment, but let's try another example. And I'm going to vary our notation just a little bit in this one. So let's say we are going to consider f of x equals actually, let me back that up just a second. Sorry, wrote down the wrong thing there, guys. Okay, so let's take a look at this one. So suppose we have little f of x equals 1/5 x to the 4th. Then we're going to say find the derivative, or find the antiderivative And a lot of times, like I mentioned, they'll want to call that antiderivative f prime with a capital F. So what we're looking for is the derivative of the function we find to give us this back. So I want both of you to think for just a moment, if you can find a function whose derivative gives you 1/5 x to the 4th. All right, so do we think we have any that work? And you can either unmute yourself and give a response, or you can type in the chat box, either way. So let's break this one apart. This one's a little bit tougher, and this 1/5 can sometimes throw us for a loop. So let's back up for just a second and think about the patterns we just saw. When we were starting with a 2x, we knew we had to have something with an x squared, because when we're applying the power rule for derivatives, our derivative should be 1 degree less. And similarly, this first example, when we looked at our derivative here and the antiderivative had a power that was 1 higher than our derivative, because when we differentiate a function that is an x cubed, we get something involving an x squared. So if we think about the power rule for derivatives, you drop a power. For antiderivatives, you go the opposite direction. You should have an antiderivative that's 1 degree higher. So if we think about that one in this case, or that rule in this case, if our starting function is x to the fourth, the antiderivative should have an x to the fifth. But try it and see if it works. Can I do a guess and check on these? If you had x to the fifth and that were your function start, your derivative in that case would be 5 x to the fourth. So does that match up what our particular function is supposed to be? Not quite, right? We have a 1/5 instead of a 5x to the fourth, or instead of a 5. So one of the things that I think is challenging for these is it's easy to kind of get lost in this notation. Don't let the little f's and the capital F's confuse you. We are trying to find the antiderivative, or the function whose derivative is 1/5 x to the fourth. So this is almost there, but not quite, right? It doesn't work, but it almost works. What we really want is a 1/5 instead of an x, instead of a 5. So in this case, think about how you would make that transition. Dividing by 5 would give you a 1 x to the fourth. Dividing by another 5, another multiple, would give us 1/5. So what it's really telling us is divide by 5 twice, or 1 over 25. So let's consider that for a second. Let's say we started with, just going across through this. Let's say we started with capital F of x is our 1 over 25 times x to the fifth. If we want to find the derivative of our capital F, we would use the power rule, and we would get 5 over 25, drop the 5, multiply by our constant, times x to the fourth. So if we reduce that, now that 5 over 25 is going to be the 1/5 that we need. So what's happening here is, if you can figure out what the power should be, we just need to manipulate the constants at that point. So let's go back to this one and make sure we're answering the question with the correct vocabulary. So what they said is, find the antiderivative capital F of x. So what we want to do after we've done our guess is remember the idea of, it could be 1 over 25 x to the fifth, but it could also be 1 over 25 x to the fifth minus 1 plus 1 plus 10. Right? We want to make sure we get the family of antiderivatives. So to do that, we just put a plus C, a plus general C. Okay, so it represents any constant, positive or negative, that we want to stick on there. So I'm going to give you guys 2 to try, and then we'll discuss. Let's see. Now I'm changing the wording just a little bit on this one, but we're going to say find the antiderivative of f of x, meaning we're finding the antiderivative, and sometimes it helps my brain to just not even think about the label or the title of the function. In other words, think about find the antiderivative of 6 x to the fifth, and then I want us to find the antiderivative of f of x equals 2 e to the 2x. So take a minute and try both of those. If you're watching, this will help me want to pause and then try it. While you guys do that, I'm going to plug my computer in here. All right, so either unmute yourself or in the chat box. Let's take a look at number one. Did anyone come up with the antiderivative in this case?
Could you do 1/30th x to the fifth?
Close, but not quite. So let's take a look at why we were thinking the 1/30th. And part of the reason thinking is because we had this manipulation of our constant in this example, right? We had this idea of going from our 1/5 to the 1/25. But this one actually is easier, right? So in this case, focus on that exponent part. Instead of the x to the fifth in the antiderivative, we're actually going to need to start with an x to the sixth. So it's good that you're thinking about how the 6 and the 5 are working together, because that's important. I'm going to title our antiderivative capital F of x. So for this one, Lainey, did you have any guesses before we go on?
I just said x to the 6.
Okay, so let's try that one. And then Grant, say what you did again, and then I'm just gonna write it down so we can kind of go back to it. So let's say guess number one, guess number two. So Grant, what was yours?
I said 1/30 x to the fifth,
Okay.
but now I understand that has to be the sixth power.
Yes. So you were actually, I think, maybe taking the derivative and then thinking about the constant manipulation. So you're right. We know you have to have the sixth power. And then on this one, if I differentiate x to the sixth, I automatically get the coefficient that I need. In other words, life is easy when you don't have to do any sort of manipulation. Now, in general, they're not always going to work out like this. So we're going to come back to a few more in a moment to keep on working with those constants so it becomes a little more intuitive. And we're going to write down some rules. So let's take a look at 2e to the 2x. So guesses for this one, and we'll write them down and investigate.
I said e to the 3x.
Okay. And Grant, what did you guess?
I didn't really think about that one.
Okay, so not yet. Okay, so let's start with this one. Okay, and then maybe we'll modify and see if we can figure out, if it doesn't work, what our next guess should be. So for this one, if we take the derivative, we have to remember the rule for exponential functions. Now, we've been thinking power functions, x cubed, x to the fifth, x squared. Now, if we think about e to the x, we'll go back to that page in a second, but we know the derivative of e to the x, it's the only function whose derivative is itself. And then if we have something like the derivative of 3 to the 5x, this involves chain rule. We have an inner function of 5x, but we have to do e to the 5x times the derivative of that inner to give us 5, or 5e to the 5x. So every time we're thinking about an antiderivative, we have to practice our derivative rules, which is really good practice, because when we think about our cumulative final, you guys, by practicing all these antiderivatives, are going to be great. We're going to remember all of those derivative rules that we studied in that second unit. So let's think about e to 3x. In this case, our derivative is going to be e to the 3x. So think about this guy as your inner function. So we have e to the power, and then times the derivative of the inner. So in this case, 3e to the 3x. All right, so Grant, refine the guess, because notice it didn't match up. What do you think we need to try next?
Could you repeat that? Sorry.
So this one didn't work because notice the 3e to the 3x didn't match up. Okay, what would you try next?
I'm not really sure.
Okay, so let's break it apart a little bit so I can show you where I'm looking at this. Notice in this case, we have some good things about Laney's guess. It didn't match up exactly, but it almost has the right form. Notice the coefficient and the power match up. They're both 3s. And in the original function, the coefficient and the power match up. They're both 2s. But what we really want is this 3 to be a 2. So if I were taking a guess, I might say, well, let's replace the 3, since the 3 popped out again in my answer, with a 2 and see if that'll work. Then we're going to develop some rules too to help us out. But let's say I guess e to the 2x. So then if I differentiate, I get e to the 2x, so e to my power, and then chain rule says multiplied by the derivative of that inner, so times 2. So now when we compare, oops, sorry guys, when we compare, oh, that looks terrible now. That 2e to the 2x matches up with what our original function was. So again, I think here too, the letters get a little bit confusing. We started with find the antiderivative of f of x, and then the general notation is to use a capital, or sometimes to not even do anything at all. So in this case, we found that the correct capital F of x was e to the 2x, or the correct antiderivative is this. And then when we were able to check it, it checks because the derivative of that gives us back the function we started with. So let's sum this up. I'm actually going to get rid of the stuff since we just used it so it stays in the same place. So what we want to say in this case is, not only could you have e to the 2x, but you could actually have any set of constants. Like you could have e to the 2x plus 5. If you had a plus 5 out to the end over here, the derivative of that 5 would be a 0. So you can always add that constant, even if you're not working with a power function. So e to the 2x plus c is the antiderivative for our function. Now, if you're having trouble with the capital parts in the lowercase, just take them off. E to the 2x plus c is the antiderivative of 2e to the x. 2e to the 2x. So what's tricky in this case? The tricky part so far is constants. So I'm going to give you guys a sequence of problems, and we're going to try to continue to guess and check until we feel like we've narrowed down on what's going on and can think about the rules. So for each of these, find the antiderivative for each function. Okay, so number 1, your function is going to be x squared. Number 2, let's say x to the 4th. X to the 5th. And x to the 10th. So I want you to think about those for a second, and then we'll take a look at your guesses. Notice each of these are power functions. I didn't mix any exponentials in yet because those can be a little bit trickier, and we're actually going to see a different rule for those exponentials. All right, so do we have some guesses for number 1?
You could do 1/3 x to the third.
Okay, so and I'm going to write these as capital F of x, thinking about just notating our antiderivative. 1/3, say it again. 1/3
X to the third.
a third. Okay, Lainey, do you agree?
Yes.
Okay, and I'm going to go ahead, just so we don't forget, I'm going to go ahead and put plus c on the end because we know the plus c is going to appear on any general family of antiderivatives. So let's take a look. Lainey, what did you do for the next one? Lainey, did you have a guess for the second one?
Yeah, it was 1/5 x to the 5th, and then plus c.
Okay. And then, Grant, did you get to number 3?
Yeah, it'd be 1/6 x to the 6th plus c.
Okay, so what I did with these ones, and hopefully you got the last one, right, once you get a few of them, now we can see the pattern going on with this one. Hopefully you did 1/11 times x to the 11th plus c. And for these ones, what made this easier was that we didn't have any constants in front of our original. So there's just the 1. So if we can remove what's causing us problems, sometimes the constants might make our function's antiderivative easier. For example, when we started with our very first one, or maybe let's do this one. The antiderivative of 2x is x squared, because when you differentiate x squared, you get 2x. Like we can do that pretty quickly. But having a 2 to start with can mess up what we're thinking in terms of going the other directions. So in other words, when we put that 1/5 there, it made it hard to think about. So if we simply eliminate the constants and just think about basic power functions with no coefficient other than 1, then we see the pattern. Add the power, and then 1 divided by that new power is our new coefficient. So let's think about how to handle another example. So let's say I give you number 5. And I tell you that we're going to have 3 x to the 5th. Can we find the antiderivative? Now, let's walk through this one together. If we think about just x to the 5th, well, this is similar, or should be similar, to what we did in number 3. In other words, remove that 3, and our antiderivative should be 1/6 x to the 6th. Or some people might prefer to write it as x to the 6 over 6, same thing. So in this case, think about all we're missing is that constant. When we did derivatives, we could pull the constant out in front, ignore it, and differentiate all the rest. Turns out, because you can do it for derivatives, it works in reverse for antiderivatives. So what we're going to do is hold that constant. And then think about what our solution was if we just had the x to the 5th. Now, you don't have to necessarily carry that 3 over the constant, because 3 times a constant is still a constant. But now, if we take a look at cleaning this up, 3 divided by 6 gives me 1/2. So I could clean this function up. And let's see, I think I inadvertently here, guys, made this a little bit sloppy. This was actually my antiderivative function here. I put an equals, but then didn't write the capital F of x. So we could write 1/2 x to the 6th plus c. So then start there. If we had 1/2 x to the 6th, if we differentiated that, 6 drops in front, 6 over 2 gives me 3, and then I've got x to the 5th. So one of the key things to help us is if we don't automatically see what's working, remove the constants and go back to your basic power function. So let's try another one. It's still going to be find the antiderivative. And a lot of times students will say, oh, f of x, something like that. Okay, so in this case, let's say our function is 1/2 x to the 8th. And let's go ahead and give another one really quickly. Okay. So our second one, 3x squared. So try both of these, and then we'll compare. All right, are we ready to go over these ones? Let's see what our guesses are for number 1. So number 1, Lainey, what did you put for your capital F of x?
1/18 x to the 9th.
And also on plus c. Grant, did you have the same thing or something different?
Yeah, I had the same thing.
Okay, that's positive. Well, let's double check and make sure we agree and think through the process on this one. So if I were looking at it, I probably would have said, hey, I need to think about, hopefully you guys say the same thing. I need to think about, well, I'm really gonna have an x to the 9th over 9th kind of coming from my x to the 8th piece. Because if I differentiate x to the 9th over 9th, I get over 9, I get x to the 8th. And then if I want that 1/2 back in, I'm going to need to think about pulling it out and putting it back. Okay? And then my 2 times 9 gives me 18, so it works. Now, checking, we always go back and do the extra check. If you differentiate your function, you would get 9 times 1 over 18 x to the 8th. The derivative of the constant gives me 0. So I get my 1/2 x to the 8th. Okay, and that's back where I started, so I know it's good to go. The nice thing about antiderivatives is we should be able to check each and every one. Once we find our antiderivative, differentiate it, and we get back where we started with. Now, how about our second one? Grant, did you get to do a guess for that one?
Yeah, you just have x to the 3rd plus c.
Beautiful. And we'd actually looked at this one before, but when we did this one and I asked, well, what function do you differentiate to give you 3x squared? We're kind of already thinking about that x cubed. But in this case, if you're kind of walking through this rule, what we can do to kind of break it apart is to say, okay, well, if I had just x squared, then my antiderivative should be x cubed over 3. But then I still have this constant of 3 in front. So notice when you have that 3 over 3, it cancels. So this idea of still isolating the power rule or the power rule part and going backwards and then playing with the constant afterwards still works, but you can also kind of do the first method we did. So what we're going to do now is introduce a little bit of new notation. It is cumbersome to deal with the capital F, the little f, and writing out these words every time. Agreed? It's just, nah, we don't want to do it, right? And the F's, F primes, capital lowercase, cause a lot of confusion potentially. So what we do is make a shortcut. what we're going to do is introduce a symbol for the antiderivative. So when we want to find the antiderivative of this function, the antiderivative symbol, it's also called an integral symbol, looks like an elongated S. We'll talk about y and s later. But we'll say the antiderivative of 3x squared, and then we put a dx. The dx tells us what the independent variable is. For right now, it's matching the x that we saw. In other words, it's find the antiderivative with respect to x. So that's much more compact. The antiderivative of 3x squared with respect to x is x cubed plus c. And then the other one, the 1/2, so that should match what we did with the sky. So any questions about that notation? So let's go ahead and let's recap the rules that we just discovered. It's much easier to write the rules of the summary using our new antiderivative notation. So here's what our rule would say. If we are looking at, and I'm going to leave a little bit of space on purpose here, because we're going to go back and put some conditions on this. Let's say we're looking at x to the n. Here, n represents a power. Now, so far, we've only looked at positive powers and whole number powers, like 2, 3, 5. We're going to consider the other ones. But if for just a minute you're focusing on those positive whole number powers, think about what we did. The power should go up by 1. And then you divide by that same new power. This is called the power rule for antiderivatives. Now, in this particular case, I want you to consider what happens if your n was -1. So if you put -1 in there, -1 as a power is a 1/x. But if you tried to put n equals -1 in here, you're going to have division by 0. So it actually turns out that this rule, not only does it work for the positive powers we've looked at, but you can extend it to negative powers as long as your power isn't -1, and you can also extend it to fractional powers. So this one is going to be our single most important rule that we're going to see for chapter 7, particularly 7.1 and 7.2. Now, let's go ahead and do one more example before our break. Hold on just a second. All right, guys, sorry about that. But let's take a look at another example with our power rule. So for this particular example, let's say we want to find the antiderivative of square root of x with respect to x. So what we're saying is, tell me the function whose derivative is the square root. And this looks a lot different than the ones we've looked at, but our key is, just like in the derivative section, we've got to convert that power back to a rational power. Now, our power isn't -1, so the power rule for antiderivatives should still apply. So think about what we did in the other ones. Add 1. If we add 1 in this case, think about our new power is 1/2 or 3/2. Usually we'll prefer the fraction in this case. But then you always divide by that new power. But this looks awkward. When you divide by that 3/2, dividing by 3/2 is the same thing as multiplying by 2/3. When you write it out like this, notice what happens. When you take the 3/2 and drop it down in front, 3/2 times 2/3, the 3's cancel, the 2's cancel. So our coefficient is 1. Notice there's nothing up here. And then when we subtract 1, we get x to the 1/2. So a little bit trickier, but the same idea. Questions here? Okay, I think I said one more, but let's do one more additional one, and then we're going to take our break. So let's take a look at the antiderivative of 1/x² with respect to x. So this is our first negative exponent, but the rule works for negative exponents as long as it's not -1. And in this case, this is the same thing as the antiderivative of x to the -2 with respect to x. So we should be in good shape. So in this case, if you think about your power, adding 1 to your power actually brings you up to -1. Don't let that -1 confuse you, because that is going to be our new power, and then that's what we divide by. So think about, if this were a +2, we would have x³/3 to the new power divided by the new power. Here, our new power is -1, and we divide by that -1. Don't forget our plus c. And then clean this up. Here, dividing by -1 is the same thing as just having -x to the -1 plus c, which is the same thing as -1/x plus c. Now at this point, you're probably saying, okay, we need to check this. So in order to check it, we could differentiate -1/x, and we should get +1/x². So what I want you to do is check this, and then we're going to do a little bit more practice. But let's go ahead, and since it's 10:50, let's stop and take our break. When we come back, let's come back at 1 o'clock. We'll check this one in particular, and then we'll go on with some more antiderivatives. All right, so I'm going to stop this. When we come back, we'll take questions and then also continue on with the rest of our rules. I will go ahead and end our meeting, and then I'll reopen it up.